My name is Sam Bratsman. This is Gabriella Lawson. We're both master's students at BYU right now, finishing up our research. We've been working on a similar project in Utah Lake, looking at nutrients and how they're related to algal blooms. It is pretty science heavy. We're talking a lot about nitrogen and phosphorus, so just bear with us. You can talk to us afterwards. We're right over here. But before we get started, of course, we want to acknowledge all the people that have helped us with our research. We have a ton of great collaborators. And those who have funded us, right, BYU and the Utah Department of Environmental Quality have been instrumental. And of course, we want to recognize the Timpanogos Nation as the original inhabitants of the land.
Great, thank you, Sam. So blooms on Utah Lake are made up of phytoplankton. And phytoplankton consists of cyanobacteria, which are prokaryotic organisms that produce really harmful toxins that are damaging to people and animals, as well as green algae, diatoms, and dinoflagellates, which are all eukaryotic organisms that do not produce any toxins but are still damaging to the overall ecosystem when in abundance. All of these organisms are photosynthetic, and that means that they rely on light for their power. In addition to light, they also need nutrients, specifically nitrogen and phosphorus. When we talk about nitrogen and phosphorus, though, not all forms are created equal. Some are more bioavailable than others. So we're going to be talking in terms of dissolved inorganic nitrogen, or DIN, and soluble reactive phosphorus, or SRP. And our big questions that we set out to answer were, what nutrients are influencing blooms and when, and what nutrient concentrations will reduce phytoplankton? So our lab has been studying Utah Lake for a few years now. We've done multiple studies monitoring lake seasonal water quality characteristics and bloom dynamics across several different lake locations, and most recently we conducted bioassays where we collected water from 3 different sites across Utah Lake: Provo Bay, which is highly impacted by urbanization, the east, which is moderately impacted by urbanization, and the west, which is lightly impacted by urbanization but will continue to be more impacted by urbanization as we progress into the future. Water from each of these sites was taken and were subjected to nutrient additions or dilutions and then incubated in a common garden. Now we'll talk a little bit about light. So Utah Lake is quite shallow and turbid, but despite this turbidity, light still penetrates into the water column at depths of 20 to 50 centimeters based on Secchi depth reads. The deepest depths occur in the summer and late summer when phytoplankton are most active. So while light does limit phytoplankton, and we accounted for this limitation by adding a shade cover and the plastic cubitaners reducing light by 45%, light limitation is not stopping phytoplankton from responding to nutrient additions. So here are some of our results. Right now what we're looking at is chlorophyll A concentrations and phycocyanin concentrations. Chlorophyll A is an indicator of phytoplankton biomass, and phycocyanin is our indicator of cyanobacterial abundance. So you can see that there are clear seasonal trends, and we see that Provo Bay especially supports a lot of phytoplankton, followed by the east, especially in those summer through fall months, peaks in late summer. And the east and Provo Bay support the most cyanobacteria. The east especially, we see a large peak in those summer months. Now, when we added our nutrient additions, we found that the nitrogen and phosphorus increased phytoplankton abundance in the summer, late summer, and fall across all lake locations. And we found that phosphorus alone increased cyanobacteria abundance throughout these summer months. And we found that nitrogen in the east and Provo Bay, so those areas that are impacted by urbanization. And we also found that nitrogen alone increased cyanobacteria abundance in the west, the area that's less impacted by urbanization. Now, how does this relate to toxin concentrations? Well, it's pretty complicated. So you can see here in the east for microcystin, there's a peak in the summer month that corresponds to a peak in phycocyanin concentrations in the east. However, the rest of the toxin concentrations do not correlate very well to the biomass that we were observing. So it's not a great indicator to say, oh, there's a lot of phycocyanin, there's a lot of cyanobacteria, that means we're going to see a lot of cyanotoxins. because we're actually seeing in the spring, for example, very big peaks for cylindrospermophs and anotoxin, even microcystin is quite high when our phycocyanin levels are really low and we're not really seeing bloom conditions. Great, Sam, take it away.
So one of the questions that we wanted to answer, right, is at what level of nutrients are we going to see these algal blooms? And we set out to answer this question with a specific experiment in the middle of last summer, where we diluted lake water samples and added nitrogen or phosphorus or both, just to see how the algae would react and other organisms would react to that, how much growth there would be. And this is the results of that experiment. I'm going to be looking a lot at this chlorophyll A graph and the nutrients over here. So we can see from the chlorophyll graph, there's a pretty clear division between two groups there, where there was more growth with the red, yellow, and blue, and below them, there was less growth. That's what we want, right? And then looking at the nutrient concentrations from each of those groups and the DIM, or the nitrogen that's available, there's a pretty even split where there's high concentrations on each side and there's low concentrations on each side. So there's not a big correlation for nitrogen. But if we're looking at SRP, or the phosphorus that's available to these organisms, there's a pretty clear correlation. These groups that had less growth in them, they had really small amounts of phosphorus. It was about 0.005 milligrams per liter, which is very small. But above the line where there actually was growth, there was always higher amounts of phosphorus. So we know that the phosphorus is a big control on how much growth we have and how intense the blooms are. So knowing this, we looked at some of our seasonal data. And these lower concentrations that we set as kind of thresholds for how much growth is going to happen. The thresholds we set for SRP, right, being 0.005, as I mentioned before. And looking at our seasonal data, we are at or above that concentration for almost all of the year, especially summer to late summer, where we see we're way above our concentrations. And there's a lot of algal growth in that time period. For DIM, right, we're about at or around that threshold that we set, so we're not as worried about these high concentrations of nitrogen. Except for Linden Marina in late summer, I don't know what happened, if anyone knows. But in knowing this, we propose that there needs to be a dual management strategy where we focus on maintaining levels of nitrogen, specifically DIM, right? And lowering levels of SRP, or phosphorus, that's in the lake. In doing this, we can reduce the amount of algal blooms that occur in the lake and the intensity of the algal blooms. We think this management strategy should be in terms of DIM and SRP, the nitrogen and phosphorus forms, since those are the most bioavailable. We converted our thresholds here to total nitrogen and total phosphorus. That is a rough estimate, but we believe there needs to be more research into kind of the ratios between total phosphorus and SRP. We know that can be kind of strange sometimes. And also further experiments to figure out exactly where the threshold is. We have a rough idea, but we want a better idea, right? And also with toxins, we would like to know what are the major controls on that. So this is our presentation. Again, come talk to us if you want to learn more. I know that was a lot to take in 7 minutes, but thank you for your time.